Hi students, welcome to Max Point of View. Today we are going to understand the concept of radioactivity part A, that is nothing but structure of an atom and radioactivity. When it comes to structure of an atom, that is very simple concept to understand, but when it comes to radioactivity, that is very much important because that is easy to understand. The emissions are easy to understand, but the trick part you should know. When it comes to the equations, we are going to understand how to solve the equations. Very easy, just an addition and subtraction. If you learn the trick part, then it is very easy to solve any equations. So after understanding the concept, okay, we are going to solve each and every theory question from this chapter. There are no numericals, only theory questions. But if you are using older versions of textbook like before 2025, a 2024-23 version edition, okay, in that textbook we have got only 30 theory questions, but in 2025 okay version there are 51 questions. So we are going to solve each and everything, learn everything, then you will get the complete knowledge. So the main thing about this chapter is the give reason questions and the equation and simple concept. That's it. Whenever students are trying to learn from the textbook, they don't know how much to study, what not to study, all those things. See, in the textbook they have many things and a few things are not there in the textbook, and students doesn't know what to study and what not to study. See, this is very simple. So when it comes to structure of an atom, in the first page of radioactivity, this is the concept: structure of an atom and structure of nucleus. If you know this much, then you have know everything about the structure of an atom and structure of nucleus. This is what you require, and many things apart from that, and remaining things are not at all there for the syllabus. Okay, listen. First we'll understand one by one. Don't worry about all these things. So I'll teach you how to remember also. Listen, structure of an atom. When it comes to atom, keep this in mind. When it comes to atom, three things we are going to talk: protons, neutrons and electrons. They are never going to ask you to draw the structure of an atom, because see, in physics you cannot expect very simple diagrams and all. Whatever the questions they are going to ask, maximum give reason questions only and few simple numericals. So this diagram they are not going to ask, but one thing you need to remember is what are the three constituents of atom. Three constituents. They may ask you three directly, or they may ask you what are the main constituents of atom. If they are asking like that, the three constituents of atom, the main constituents of atoms are protons, neutrons and electrons. Keep this in mind. So when it comes to atom, three constituents, but when it comes to nucleus, there are only two constituents, that is proton and neutron. So in atom, proton, neutron and electron. When it comes to only nucleus, proton and neutron. So togetherly, proton and neutron togetherly called as nucleons. Keep this also in mind. So proton and neutron togetherly called as nucleons. So the two constituents of nucleus is proton and neutron, or else you can call it as nucleons. When it comes to atom, proton, neutron and electron. See, these are the charges and their masses. Listen, when it comes to charges and their masses, based on the previous year papers, they are never going to ask the values, because when it comes to remembering values, they are never going to ask any questions. So just for a safer side, we are going to learn charge of electron and charge of proton. Listen, here the same value 1.6 into 10 power minus 19 C. Here also it is 1.6 into 10 power minus 19 C, but it is negative, this is positive. Okay, then when it comes to mass of an electron is less than the mass of proton. Keep that in mind. Mass of an electron is less than the mass of proton. So it is 9.1 into 10 power minus 31. You may be thinking it is just 1.67 and this is 9.1. How can sir say that mass of an electron is lesser than mass of proton? See, not only this value 10 power, that is also very much important. 10 power minus 27, but here 10 power minus 31. So mass of an electron is less than the mass of a proton. Then when it comes to this one, neutrons. Okay, neutrons, they are neutrally charged. Okay, they are not even positive, they are not even negative. So the charge is 0 C and the mass is equal to the mass of the proton. So if you know this much about structure of an atom and structure of nucleus, that is enough to get good marks. So based on this one, they may ask you 1 or 2 mark question, just what are the constituents of atom and nucleus. You have to be very careful. Now we are going to learn about a very important terms, and don't get confused with the words here. I am going to explain each and everything in a proper way. Listen, first Z. Z is nothing but atomic number. Keep that in mind. What do you mean by Z? Atomic number. Because in this chapter we are going to use atomic number and mass number. Mass number is also called as atomic mass number. This is atomic number. See, never use this short form in the exam because they are going to reduce 1 marks. Keep this in mind. Whenever you use short forms in the exam, that too in physics, they are going to reduce 1 mark. Why? Because we require only precise answer. The answer will be of, most of the time it will be of 1 word. So if you shorten that 1 word also, you are not going to get any marks. That's why, so never ever use short forms. Use NUMBERE. Okay, atomic number, and this one also called as mass number, okay, or atomic mass number. Anything is fine. This is atomic number, this is atomic mass number or mass number. In the textbook they have defined it as mass number. We can use mass number, but whenever I use atomic mass number, that is nothing but just mass number. Keep that in mind. This is the term we use for atomic number, and this is for atomic mass number. What is atomic number and what is atomic mass number? That is what we are going to learn here. Listen, see, atomic number is nothing but number of protons. It is completely related to protons. This is completely related to number of protons. So atomic number is nothing but number of protons. Then atomic mass number or just mass number, it is the sum of both protons and neutrons. Both protons and neutrons. What do we call protons and neutrons togetherly? Nucleons. Keep that in mind. That is what we have learned in the first concept, first slide, right? Next, listen. This is how we write it. This will be one of the element, okay, one of the element in the periodic timetable. Don't worry, you don't have to by heart anything. So we are going to give everything. You just need to understand and do the equation, solve the equation. That is what we are going to learn in the upcoming slides. Now listen, this is how we write. This will be the element, and we are going to write the atomic mass number. So A represents mass number or atomic mass number. So A represents mass number. Whatever the mass number is there, we are going to write it here, and this one we are going to write it here. What is this? The number, atomic number, just this number of protons, and this will be number of protons plus neutrons. So you need to know this basic, very important. I'll give you one example. See, element 2311. So this 11 represents number of protons, and this 23 represents number of protons and number of neutrons. How to find number of protons and neutrons? That is what we are going to learn here. Okay, listen. Mass of an atom is equal to mass of a nucleus. Do you think this is correct? Because the nucleus is inside the atom, correct? The nucleus is inside the atom. Then how they are saying mass of an atom is equal to mass of an nucleus? Why? Because the mass of an electron, see, inside a nucleus we have proton and neutron, like this. This is the nucleus, proton plus neutrons. Outside that we have many electrons, correct? So here they are telling the complete mass of an atom is equal to mass of an nucleus. Why? Because outside we have electrons, right? The mass of electrons are very negligible. The mass of electrons are very negligible. If you remove the mass of an electron, the remaining constituents are this one, proton and neutron. So proton and neutron are inside the nucleus. So mass of an atom is equal to mass of a nucleus. Keep this in mind. Why? Because the mass of electrons are considered as negligible. That means they are not going to add the mass to the atom. So if you remove the electrons, we have only left with protons and neutrons, and those are also inside the nucleus. That is nothing but mass of nucleus is nothing but the mass of an electron. Next, Atom is electrically neutral. Atom is electrically neutral. What do you mean by neutral? Neutral means it is neither positive neither negative. Why? Because see, atom consists of both protons, electrons and neutrons. We know neutrons are there is no charge for a neutron, that is charge is 0. But when it comes to proton and electron, electrons are negatively charged, protons are positively charged. We know the charge number is also equal. So what is the charge of an electron? Minus 1.67 into 10 power minus 19. The charge of a proton is plus 1.67 into 10 power minus 19. The value is same. Electrons are negatively charged, protons are positively charged. So plus and minus is nothing but neutral. So the complete atom is electrically neutral. This is how you can explain them. If they are asking why the atom is considered as electrically neutral, this you can answer in an easier way. Now, number of electrons is always equal to number of protons. Keep this in mind. Number of electrons for any element, number of electrons is equal to number of protons. We learned that number of protons are nothing but atomic number. So number of protons is considered as atomic number. If number of protons are equal to number of electrons, this is also considered as atomic number. Keep this in mind. See, they may confuse you. Number of electrons will be given, so you have to assume it as that is nothing but number of protons. Okay, if number of protons, the total number of protons in an atom is nothing but atomic number. This is how we can find the values. Next, number of neutrons. See here, I told this is a number of protons, nothing but number of atomic number, and this is atomic mass number. How do you find the number of neutrons from the given example? Listen, we know the z value here is 11, correct? The z value here is 11 and a value here is 23. Z represents number of protons, a represents number of protons plus neutrons. Then how we can find the number of neutrons in an atom? That is nothing but a minus z. So here a here is 23, z here is 11, 23 minus 11, that will be 12. So number of protons in this concept example is 11, number of neutrons are 23 minus 11, that is nothing but 12. So this is how we are going to find the values. Next, during the chemical change, this is very much important. These are the note. See, in your textbook there some note points will be given, right? Do you know boxes, all those things, that also very important. So that all those things we are going to learn. See, during the chemical change, it requires low energy. It requires low energy. Okay, low energy in the form of electron volt. Electron volt, I know you'll get confused. Electron volt is nothing but one of the units of energy. You know, one of the units of energy. We know when it comes to energy, the main unit is joules. So there is a conversion between joules and electron volt. Don't worry about it. So now you need to understand one thing is, when it comes to electron volt, it is nothing but one of the unit of energy. So during the chemical change, it requires only low energy and in terms of electron volt, keep that in mind. It requires low energy and in terms of electron volt. Okay, but when it comes to nuclear change, it requires high energy and it will be in terms of mega electron volt. See, how can you convert electron to mega electron volt? 1 mega electron volt is equal to 10 power 6 electron volt. That means here the value is in terms of 1. Here it is in terms of 10 power 6. So it requires nuclear change. Nuclear change requires high energy, that too in terms of mega electron volts. So what is the difference between chemical change and nuclear change? Chemical change, there will be a change in or electrons. Okay, so during the chemical change or after the chemical change, there will be a change in electrons. Keep this in mind. There will be a change in number of electrons. But when it comes to nuclear change, during the nuclear change, there will be a change in nucleons. What do you mean by nucleons? That is nothing but The total number of protons and neutrons are called nucleons. So during the nuclear change, there will be a change in nucleons, that too inside the nucleus. So nuclear change happens inside the nucleus, but this one outside the nucleus. So chemical change requires low energy, that too in terms of electron volt. During the chemical change, there will be a change in number of electrons. That's it, orbital electrons, that meant outside electrons. Next, during nuclear change, it requires high energy and in terms of mega electron volt, and during the nuclear change, there will be a change in number of nucleons. Number of nucleons. What do you mean by nucleons? The number of protons and neutrons togetherly called as nucleons. So nuclear change happens inside a nucleus. This chemical change will not go inside a nucleus, it happens on the outermost orbits. Next, in nuclear change, A is nothing but mass number and Z is nothing but atomic number. In nuclear change, the atomic number and the mass number is conserved. What do you mean by that? So I'll give you one example. Listen. So this is just an example. Don't consider this as an actual equation, just for understanding. Okay. Okay, listen. So these are called reactants, and this is nothing but products, correct? So when the reactant is undergoes nuclear change, the mass number and atomic number is conserved. What do you mean by that? That means whenever you add these two, the upper part is called mass number. Whenever you add these two, that will be equal to this one. Whenever you add the atomic numbers of the products, okay, after the reaction, whatever the products we are getting, if you add these two, that will be equal to this one, that is conserved. So atomic number and mass number will be conserved during the nuclear change. That means in the products, whenever you add all the mass number, that will be equal to the initial mass number, and if you add all the this one atomic number, that will be equal to the initial atomic number. That is nothing but atomic number and mass number during the nuclear change is conserved. So if you know all these things, these are the basics before going to the actual topic. So if you know this much, then you have learnt everything. Now we can aram se go for isotopes, isobars, all those things. Now actually we are jumping into radioactivity concept. Till now the structure of an atom, what is the meaning of atomic numbers, mass number, all those things. Now very important, isotopes. Listen, when it comes to isotope, the definition is very simple. Same elements having same atomic number. See, atomic number, instead of using the word, I am using symbols, but in the exam you should not use symbols, you should use the words, expanded form. The same elements having same atomic number but different mass numbers, those are called isotopes. You got my point? Same elements having same atomic number but different mass number. I'll give you a few examples. Listen, these are the same elements, hydrogen, 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 having same atomic number, correct? The below one is atomic number, the above one is mass number or atomic mass number. So the above, see the above one, this is 1, 2, 3, different mass number but same atomic number, and the elements also same. These are called isotopes. You can take this one also as an example. Same elements having same atomic number, different mass number. So these are the examples for isotopes. You can use any one. Next, note very important things about isotopes. See, they may ask you the definition, they may ask you to give an example, or they may ask you questions when it comes to isotopes. When it comes to isotopes, they may ask you few important topics. These are in the note, okay, the note box in your textbooks. Listen, tin, okay, the tin, this one symbol in this one periodic table is Sn. So tin or Sn as the large number of isotopes. What do you mean by large number of isotopes? That means, see the hydrogen 1, 2, 3. So in the textbook they haven't mentioned how many isotopes the tin has, but keep one thing in mind, hydrogen, see hydrogen, how many isotopes? 1, 2, 3. But when it comes to tin in the periodic table has the largest number of isotopes. Keep that in mind. Next, there are two types of isotopes. stable and unstable. Unstable is also called as radioactive isotope. Keep this in mind, because in the exam they may use unstable or radioactive isotopes. So there are two types of isotopes, stable and unstable. Unstable is also called as radioactive isotopes. What do you mean by stable? See, this in stable, the number of neutrons, the number of, see here, the number of neutrons and protons both will be there. Here this is P plus N and this is only P, correct? The number of protons will be equal to number of neutrons. Number of protons will be equal to number of neutrons. So here the protons are 1. Here we have both protons and neutrons. We already know proton is 1, correct? This P is 1. The remaining one in this 2 is again 1. So number of protons is equal to number of neutrons in stable isotopes. Unstable isotopes are also called as radioactive isotopes. Here the number of neutrons will be greater than the number of protons. Number of neutrons will be greater than number of protons. I'll give you an example. Listen. Here this is the atomic number, that is nothing but Z. Z is equal to 92 and A is equal to mass number is equal to 235. We know in Z we have only protons, so protons is equal to Z, that is nothing but 92. But when it comes to neutrons, how to find the number of neutrons? A minus Z. If you subtract it, we'll get the answer. So number of neutrons is equal to A minus Z, 235 minus 92, that is 143. See here, number of neutrons are 143, number of protons are just 92. So here when it comes to these kind of examples, these are called unstable isotopes or radioactive isotopes. So where the number of neutrons are greater than the number of protons. So this is an example for stable and unstable. If you know this much about isotopes, that is enough. Now we'll learn about isobars and isotones. Don't worry, we are going to learn one by one, then only you will understand everything. Finally we can compare them to understand them in an easier way. Now listen, isobars. See, isotopes have same elements, but here it is termed as different elements. So different elements, same mass number but different atomic number. That was isotopes was same elements, same atomic number but different mass number. This is completely different. So different elements, same mass number and different atomic number. Now listen, sodium, you can take an example of this one, sodium and magnesium, 11 23 12 24. So different elements, same mass number but different atomic number. This is an example. You can take this as an example. In the exam you can write any one. Now listen, different elements, same mass number, different atomic number. That's it. Now there is a concept called mirror isobars. In some isobars, okay, the number of protons, so you will take an example of this one only. Number of protons is here. See, number of protons here it is 11 and neutrons it is 12, correct? How to find the number of neutrons? This minus this will get the number of neutrons. Compare this one here. P is equal to 12, N is equal to 11, correct? 12, that is number of protons, and this minus this will give us the number of neutrons. In some examples, in some isobars, if the number of protons, okay, are interchanged, number of protons are interchanged with number of neutrons. See here, the number of protons are 11 and here the number of protons are 11. Here the number of neutrons are 12, here number of protons are 12. They are interchanged, right? The number of protons and number of neutrons are interchanged in some isobars. Those are called mirror isobars. That is a definition. The number in some isobars, the number of protons and number of neutrons will be interchanged. That is nothing but mirror isobars. Now that's it about mirror isobars. Now we'll go to isotones. Isotones, when it comes to isotones, sometimes it will be a little confusing, but if you focus, you can get it properly. Listen, different elements, again both will start with the different elements. Here we had same mass number, and different atomic number. But when it comes to this one, both atomic number and mass numbers will be different, but as same number of neutrons but different number of protons. Same number of neutrons, in both the cases same number of neutrons will be there but different number of protons. So this is the definition of isotones. I know it is a little confusing. So different elements having both atomic mass number and atomic numbers are different, but they have same number of neutrons. In both the cases same number of neutrons, I'll show you how, and different number of protons. Listen, different elements having different atomic number and mass number, different mass numbers and different atomic numbers, these are called isotones. And here the one important point is the number of neutrons will be same. How can we find the number of neutrons and protons here? See, protons is equal to this value, that is Z, correct? Neutrons, this minus this, that is nothing but 20, correct? When it comes to this one, protons is equal to 20, neutrons will be equal to 40 minus 20, that is 20. In both the cases, see, same number of neutrons, but as same number of neutrons but different protons. See, protons, this is 19 and this is 20. This is the definition and the example of isotones. So if you know about all these things, so if you can learn all these things in an easier way with an example and all those note points, then you have learned everything about isobars, isotones and isotopes. That's it. Now we'll talk about what is radioactivity and who found it. So Henry Becquerel, it was an accident actually. So in 1896, he left some photographic plates and some uranium salts which was wrapped by the black paper. So uranium salts were wrapped by a black paper, and he left some photographic plates in his lab. When he went out, after coming back after next day, he got to know the photographic plates were damaged. It was affected by something. Okay, it was damaged by something and he did not know by which substance it was damaged. So based on some observations, so he took out some other elements and he observed that whether the photographic plates are affected or not. And while doing this trial and error method, he got to know uranium is the culprit. Uranium is the culprit. Even though it is wrapped by a black paper, it is emitting some radiations. So, and the conclusion he got it, they emit radiation. Which emit radiations? The uranium. And so these radiations can pass through black paper, glass, even wood. So, and some other materials. Now these radiations, whatever the radiations emitted by the uranium, are also called as Becquerel rays. They are also called as Becquerel rays. When it comes to radiations, there are three types of radiation: positive, negative and uncharged. Positive radiations are called alpha, negative radiations are called beta, uncharged, neutrally charged, those are called gamma. Alpha, beta, gamma. So alpha, beta and gamma. Now definition, how can we define radioactivity? Very simple. Next, natural radioactive substances. What do you mean by that? In a periodic table, after 82, the atomic number after 82, that is nothing but after lead, whatever the elements are there, those are called natural radioactive substances. Why only those are considered as natural radioactive substance? Because in those elements, the number of neutrons are much more than the number of protons. Number of neutrons are much more than the number of protons. But when we take the example of sodium, see, if I take example of sodium, here the number of protons are 11, the number of neutrons are 12, correct? But this is not considered as natural radioactive substance. Why? Because number of protons are less than the number of neutrons. But how much? Only 1. So this 1 or 2 difference will not be considered as natural radioactive substance. The number of neutrons and the difference between number of neutrons and protons must be greater. Then only it is considered as natural radioactive substance. So what do you mean by natural radioactive substance? The atomic number after 82 in a periodic table are considered as natural radioactive substance. Why? Because the number of neutrons are much more than the number of protons. So these are the some basics about radioactivity. Some important things about radioactivity. Radioactivity is called as nuclear change. Radioactivity is called as nuclear change. Why? That is what we are going to learn. And a few more facts. Listen. Any physical change, that is pressure and temperature, if you increase or decrease the pressure or decrease the temperature, those are called physical change. Any chemical change like heating, freezing, electric field and magnetic fields will only affect all these things. Any physical change and chemical change will only affect the orbital electrons. See, this is the nucleus, correct? So these are the electrons. So these physical or chemical changes will only affect or change the number of electrons, that those are nothing but orbital electrons, and they will not go inside, they will not do any change inside the nucleus. No change inside the nucleus because of physical and chemical change. They only change the number of electrons, that is nothing but the orbital electrons. So, and nature of radiation. Listen, this is why any physical change and chemical change are not considered as nuclear change. Only radioactivity is considered as nuclear change. Keep this in mind. Why physical or chemical changes are not considered as nuclear change? Because they will only change the number of electrons, orbital electrons, that's it. The nature of radiations like alpha, beta, gamma, positive, negative, uncharged, all those things, and rate of decay. What do you mean by decay? The disintegration, the reduce in mass. Okay, that is nothing but decay. Rate of decay means whether it increases or decreases. Those things, the nature of radiations and nature of the rate of decay will not depends upon the change in orbital electrons. The change in orbital electrons, it is completely depends upon the nucleus. It is completely depends upon nucleus. That is why radioactivity is called as nuclear change, and physical and chemical changes are not considered as nuclear change. Now, assume there are many atoms. In many atoms we have many nucleus, correct? Each and every atom will have one nucleus, correct? So assume there are many atoms in a substance, and we cannot predict which nucleus of which atom is going to leave the radiations, is going to emit the radiations. So there is no law or there is no way to predict which nucleus of an atom is emitting the radiations, and this is why it is also called as why radioactivity is also called as random phenomenon. Why? Because assume there are many atoms in a substance. In each and every atom we have one nucleus, correct? We cannot predict which nucleus of which atom is emitting the radiations. So that is why it is called as random phenomenon. So these are the facts about radioactivity. Now we have learnt this one, history of radioactivity, Henry Becquerel, correct? The natures, correct? And why those are called natural radioactive substances. Then some facts, why it is radioactivity is a nuclear change, why not physical or chemical change? Why? Because physical and chemical change only changes the orbital electrons, not the nucleus. But the nature of radiation and rate of decay does not depend upon the change in orbital electrons. It completely depends upon the nucleus. That is why it is called as nuclear change. And how can we predict which nucleus is emitting the radiations? No, we cannot predict. That is why it is called as a random phenomenon. That's it. We got to know about radioactivity and the emission because of the Henry Becquerel. After him, Rutherford in 1903 conducted some experiments so that we know there are three radiations comes out of a radioactive source. Assume this is a radioactive source. From this source we'll get three radiations, alpha, beta and gamma. We didn't know the direction of them, alpha, beta, gamma directions, in the presence of magnetic and electric field. This experiment is conducted by Rutherford. When these magnetic and electric field are considered as physical changes, okay, and this source is considered as nuclear change. We know the reason, we have learnt it. Now listen, these physical changes, okay, when this source is experienced by a magnetic field, first we'll learn magnetic field and then we'll go for electric field. This is a very easiest topic, and based on this one diagram based problems will be asked, but it is very easy to draw the diagram. I'll teach you. Listen, when the magnetic field is above the source, when the magnetic field is above the source, then see, three radiations will come. One radiation will always go in a straighter way without deviation. Without deviation, that is nothing but gamma. One ray in both electric and magnetic field, without deviation, it will emitted by the source, that is nothing but gamma radiations. And one source, okay, one source will slightly deflects, that is nothing but alpha, see, this is slightly deflect and it is heavy. This is the main reason they are going to ask one question, why alpha radiations are slightly deflected. Why? Because they are heavy particle, and more deflection we can see in beta radiation. They'll ask one more question, why beta radiations are more deflected, or which radiations are more deflected and why? Beta radiations are more deflected, okay, why? Because they are light particles, and alpha is positive, beta is negative, gamma is uncharged. This is the emission of radiations. This is the diagram they are going to ask when the magnetic field is above the source, okay, in upward direction. If the magnetic field is below it, this side will be alpha, this side will be beta, and gamma radiations will be again straight. And make sure whenever you are writing the main differences between alpha and beta, how we can differentiate in the diagram. Alpha should go up, little up, and small deflection. See the deflection means the turn. Beta has more turn, that is more deflection. And if you are writing beta this side, when you can write beta this side, when the magnetic field is below the source, then beta will be this side. See, beta will come here, alpha will go here above beta, okay, alpha should go here, again gamma will be in a straighter way. Alpha is positive, whenever alpha is here or that side, alpha is always positive, beta is always negative, gamma is uncharged. Now we'll talk about electric field. When the source is experienced by a electric field, and electric field is also considered as physical change, keep that in mind. When this happens, gamma again goes in straight direction without any deflection, and so this is positive, right? So positive will attract the negative particle, keep this in mind. If this is positive, it will attract the negative particle. Which is negative here? Beta. So beta will be deflected here, and this is negative, right? So it will attract positive alpha, okay. So this side it is alpha, and this side it is beta, and this will be gamma. Sometimes they will change the sign in the exam. So this side they may give you negative, and this side they may give you positive, exact opposite. Negative if this is negative, it will attract alpha. Anyhow it is positive, that is why it is attracted beta. Keep one thing in mind, positive will attract negative, that is negative particle is nothing but beta. Negative will attract positive, that is nothing but alpha particle. So these are the diagrams. Then the only possible changes you can expect: magnetic field down below the source, here electric field, it may be negative here, it may be positive here. All those differences we are going to learn in theory solution. So if you learn theory solution, you have learned everything about this chapter. When you open the textbook, the properties of alpha, beta, gamma, that only the properties of all these things are in 3 pages. So you don't have to study all those things. If you learn this much about alpha, beta, gamma, then that is enough to get full marks. Okay, listen, the speed. First we'll talk about speed. What will be the speed of alpha, beta and gamma radiation? The speed of alpha is 10 power 7 meter per second, and this one 2.7 into 10 power 8 meter per second, and this will be 3 into 10 power 8 meter per second. So out of all the 3 radiations, which radiation speed is equal to the light? Gamma. Okay, so these two are 10 power 8, but beta is little slower compared to gamma, and alpha is slowest out of all these things because there is just 10 power 7. Next, rest mass. See, what do you mean by rest mass? So the definition of rest mass is not there in the syllabus and not in even the textbook. The rest mass is nothing but the mass of the particle which is independent, the part of the particle, only some part of the particle which is independent of motion. Okay, if the object is moving, the mass will not be affecting that. That is nothing but rest mass. See here, rest mass, here when it comes to alpha, 4 times the proton. 4 times the proton. Rest mass of an alpha is equal to 4 times the proton, and beta will be equal to electron, and here when it comes to gamma, no rest mass. Keep this in mind. Okay, rest mass of alpha is 4 times the proton, beta is equal to electrons, and gamma no mass. Charges, this is positive, negative, uncharged. This we have learnt already. Then wavelength. So what is the wavelength of alpha, beta, gamma? See, alpha and beta doesn't have any wavelength, but gamma has some wavelength. That value 10 power minus 4 to nanometer to 10 power minus 13 meter. So don't worry about the value. Keep one thing in mind, wavelength in alpha, beta doesn't have any wavelength, gamma only has wavelength. Next, deflection. So this we have learnt already with the diagrams. So deflection of alpha, beta, gamma, how it will deflect? Less deflection, okay, more deflection, no deflection, correct? So alpha, okay, will get deflected in a lesser way, beta more, and there will be no deflection in gamma. They'll ask one question, why alpha will deflect less compared to beta? Why? Because alpha particles are heavy particles, beta particles are light particles. That's why beta will deflect more. Next, ionizing power. What do you mean by ionizing power? The energy required to remove the electron from the orbit of an atom. That is nothing but ionizing power. Alpha has more ionizing power, more, okay, less and least. Out of all the 3 particles, which has least ionizing power? Gamma radiation, which has more? Alpha radiations. Next we'll come to penetrating power. Penetrating power means going through the object, So alpha as least, okay, less and more, okay. Which radiation has more penetrating power? That is nothing but gamma, which has least? Alpha. Ionizing power of alpha is opposite to penetrating power of alpha. So ionizing power is more in alpha, penetrating power is least in alpha. Next, biological damage. Biological damage completely depends upon penetrating power. If the penetrating power is more, biological power damage will be immense, okay. Less damage, more, immense damage, okay. More damage will be happen because of the gamma radiation. That's why you should not expose yourself to gamma radiations. So if you know these many properties, that is enough to get full marks. Till now we have learnt what is radioactivity, what are the radiations, alpha, beta, gamma, what are the differences between them. Now we are going to learn alpha emissions. Very, very important topic, alpha, beta and gamma emission. Alpha. So if you learn the concept, whatever the equations they'll give, you can aramse solve it. So first we'll understand the concept, then we'll go solve the example, then what are happened here, that is what we are going to learn as a conclusion. Listen, very simple. Alpha emission, whenever an unstable nucleus, what do you mean by unstable nucleus? When the number of neutrons compared to the protons are more inside a nucleus, then it is called as unstable element or unstable nucleus. Now listen, during the alpha emission what happens? This is atomic mass number, this is atomic number. So during the alpha emission, 4 units will be removed from mass number. 4 units will be removed from mass number. 2 units will be removed from atomic number. So what do you mean by atomic number? That is nothing but number of protons. So if you are removing 2 from atomic number, how many protons you are removing? 2 protons. And if you are removing 4 units from the atomic mass number, anyhow we got to know 2 protons are there. So out of 4, if 2 protons are there, how many number of neutrons are there? 2 neutrons. So completely 2 protons, okay, 2 protons, and here 2 protons and 2 neutrons. So that will be given to helium. So in alpha emission, helium will act as a product. Helium will become a product, and that is considered as alpha particle. How much ever we lost here? 4 units of mass number, that will be given to helium. 2 units of, okay, this atomic number will be lost, that is given to helium. That is why the nuclear change is called as alpha, beta and gamma emission is called as this one radioactivity. It is conserved. What do you mean by conserved? How initially how many the atomic mass number and number was there, that will be equal to the, if you add it will get the same value. That is what we are going to learn through the example. First thing you need to know is, see, during alpha emission 4 units will be lost in mass number in above part. In a below part 2 units you have to remove. Okay, whatever the number they have given, you just have to follow this. Whatever you have removed, you have to give it to the helium. So whatever the example we take, final product will be helium. Keep that in mind. Now listen, this is an example. Uranium 238 and 92, thorium. Okay, whenever it undergoes alpha emission, it gives us thorium and helium. How much thorium and how much helium? That depends upon alpha emission. Alpha emission we know, in the above part we have to remove 4, correct? In the above part we have to remove 4. If you remove 4 from 238, that will be 234. How much we have removed, that will be given to helium. That's it. Next, in the below part, that is atomic number, we have to remove 2. So if you remove 2 from 92, it becomes 90 and 2. So like in chemistry, we have to by heart many equations, right? But here you don't have to by heart. There is a rule. You have to remove 4 in the above part, 2 in the below part. Whatever you remove, give it to the helium. So this is the conclusion. How many number of protons are lost? Protons are nothing but the number of atomic number, correct? Atomic number is equal to number of protons. How much is lost? 2. So 2 is lost. Then how many number of neutrons are lost? That is, neutrons are related to the above part. Here in the above part 4 units are lost, but how many neutrons are lost? Only 2. Why? Because in this 4 last unit, 2 are already proton, the remaining 2 are neutrons. This you should know. So loss of this one, our atomic mass number, how much is lost? 4. Z will be 2. If you know this much, okay, that means you have learnt everything about alpha emission. So this is what, these equations are very important. In the theory solution, you will get to know why these equations are important, how we can solve whatever the equations they'll give. Okay, we can aramse solve it. Okay, so once after you understand this concept of radioactivity, go for the theory solutions immediately. Now we'll talk about beta emission. So here the same one element will be given. When it undergoes beta emission, see, the atomic mass number or the just mass number remains same, but protons will increase by 1. If protons is increased by 1, then the same thing is given 1. How much ever it is increased, that is nothing but electron. Okay, that is nothing but electron. So here whenever they mention E, electron, sometimes they will not give you beta emission or not. Some equations they'll give. So they'll not give you whether it is beta emission or alpha emission. How we can identify? Based on the electron. If you see electron, that is beta emission. If you see helium, He, in the previous alpha emission we learnt the final product will be helium. If they give you helium, that is alpha emission. If they give you electron, that is beta emission. Now listen, if see, the number of protons are increased by 1, correct? Then don't you think the number of protons are also increased here by 1, because mass number has both protons and neutrons? Why it is not increased? Because here whatever the mass number we have, that mass number has both protons and neutrons, So what happens during beta emission? There will be loss in neutron and there will be profit in proton. So one neutron will be lost and that will be converted into proton. So 1 minus 1 plus 1 will result in 0. That's why there is no change in mass number, and we got one proton, right? Proton is added to the atomic number. That's it. First thing, basics you should know. What are atomic mass number and atomic number? So atomic number is purely depends upon number of protons. In beta emission, one neutron will be lost, one proton will be gained. -1 plus 1, there is no change in atomic mass number, but +1 is nothing but proton. Proton is nothing but the atomic number, so it is increased by 1. This is what happens during beta emission. So parent nucleus, daughter nucleus, and that is a beta particle. Beta particle, sometimes in the exam, instead of giving like this, okay, they may give you like this. If you see this one, this is beta particle, that means beta emission. If you see electron also, that is beta emission. Now listen, well, now we'll understand this one with an example. So carbon, nitrogen, listen, 14, 6. So whenever this is given, what happens to atomic mass number? There will be no change, correct? There will be no change, but the below part is increased by 1. So 6 becomes 7, -1, 0. This is how you solve the equations. That's it. So this is about beta emission. Beta emission is easier compared to alpha emission. If you think like that, that is wrong. Why? Because in both the ways, see, in both the equations, we are just doing addition and subtraction. That's it. You should know the conditions. So in alpha emission, the above part will be lost by 4, below part will be lost by 2. But when it comes to beta emission, so above part, there is no change in above part, below part we are going to increase by 1. That's it. So now we are going to learn gamma emission. Gamma emission is one of the easiest emission. Why? Because there will be no change in both mass number and atomic number. Then what change it is happening inside a nucleus after a gamma emission? Very simple, the star. This star is converted without star. What do you mean by this star? The star represents it is in excited state. What you call that as excited state. What do you mean by excited state? It has more energy. It is converted into excited state, converted into ground state. Ground state means less energy. Excited state means more energy. That's it about gamma emission. So this is very much important, gamma particle. Okay. If in alpha emission, helium will be the alpha particle. In beta emission, electron will be the beta particle. In gamma radiation, gamma will be the gamma particle. Now what is the only change in gamma radiation? The excited state is converted into ground state. That's it. Some notes about these emissions. Listen, during the beta emission, we know electron will be released. This electron will not come from the nucleus. Keep that in mind, because in the nucleus we have only proton and neutron. This electron will not be coming from the proton or neutron. This electron will be created during the beta emission. Keep that in mind. Okay, the electron which is produced as a result of beta emission is not because of the nucleus, it is created. Okay, and any single decay. Okay, any single decay means any single emission, whenever some emission is happening, okay, beta and alpha emission is not possible. In a single decay, in single emission, either alpha or beta will emit, both will not emit simultaneously. Keep this in mind. Either beta will emit or gamma will emit, both is not possible. But beta plus gamma is possible, alpha plus gamma is also possible. Along with beta, gamma radiations can emit, as well as along with alpha, gamma radiations can emit. Gamma can emit along with beta or alpha, but beta and alpha togetherly in a single emission, it is not at all possible. Either beta radiations will come or gamma radiations will come, both simultaneously it is not possible. Keep this in mind. Now we'll understand the use of radioactivity. That is nothing but use of radioisotopes. Listen, in a medical use, as a medical use, it is used to treat diseases like leukemia and cancer using radiotherapy. Using radiotherapy, leukemia and cancers can be cured using the radiations, mainly about gamma radiations. We'll use gamma radiations for radiotherapy. Next, It is used as traces in this one diagnosis. What do you mean by traces? Traces are used in diagnosis, nothing but it is used to identify the traces are used to identify the any brain tumor or blood clot in the our body, so that we can easily cure them before it causes fatal damage. Next, gamma radiations are used in sterilization process, the cleaning process of bandages, dressing, all those things. Next, scientific use, how it is used in scientific way. Alpha particles are used in projectile motion. What do you mean by projectile motion? Nuclear reactors, all those things, they'll projectile means going up and coming down. Okay, that is simple way to explain projectile motion. Alpha, it is used in there and to estimate the size of the nucleus, and nature of the nucleus. Next, again the traces are used in scientific way in agricultural field to study the growth of plants, after using the chemical manures. So traces are used in agriculture to study the growth of plants after using the chemical manures or chemical fertilizers. Next, it is used to study the excavated materials, that is nothing but archaeology department. So these are the medical and scientific use. The final use is industrial use. The uranium 23592 is used as a fuel. Sometimes uranium is used as the fuel. Next, knowing the ionizing effect of these alpha, beta, gamma radiations, it is used in luminescent sign, that is nothing but radium sign. When the power goes off, there will be a pipe, when you break it, there will be a huge light energy that is used because of the that is used as an industrial use only. Next, beta, by knowing the beta penetrating power, we can control the thickness of paper and plastics. So these are the industrial use of radioactivity or radioisotopes. Now we'll learn about the sources of radioactive substances. So which are the main sources? Listen, the major source is the nuclear power plant. In a nuclear power plant, we use nuclear power plant to produce electricity. So nuclear power plant is the major source of the electricity. During that, the radioactivity fallout, any accident happens, these radiations will escape. That is nothing but radioactive fallout from a nuclear power plant. Next, nuclear waste. In the nuclear waste, it is based on the fuel rods. So in the nuclear plant, we use fuel rods. When these fuel rods becomes inefficient, we'll call it as nuclear waste. So this is one source of radioactive elements. Then cosmic and X-rays. So these cosmic and X-rays will be getting from the sun. When it enters the Earth's atmosphere, it still has some radioactive properties. So these are the different sources. Now we'll see the harmful effects of these radioactive elements. Listen, type 1, type 2, type 3. First we'll know about type 1. Type 1, that is short term. Okay, it's recoverable. Okay, aram se you can recover from that. Type 1 sources, that is nothing but diarrhea and sore throat. It will cause us diarrhea, sore throat. Aram se we can recover from it. Then type 2 is long term. Type 2 is limited. See, this one is limited to the person. Okay, and long term is also limited to the person. That means this, whatever the causes it is giving us, it will not be transferred from my generation to the next generation. If someone is affected from this short term or long term, it is limited to that generation only. But the type 3 is different. I'll tell you that about that. Now listen, short term and long term is limited to the present generation. It will affect only that person. So long term will cause us leukemia and cancer. Leukemia and cancer, we know. We can use radioactive elements, radiations to cure leukemia and cancer. In the same way, if we are exposed to those things, again we are going to get the same thing only. Next, these are irrecoverable. We cannot get cured from it. Okay, next, type 3, that is genetic. Genetic, again it is irrecoverable and it causes the diseases like this only, and it will pass us from generation to generation. That is type 3. So these are the harmful effects of radioactive radiations. Now we'll talk about safety precaution. That too, first we'll talk about while establishing a new power plant. So before building a new power plant, these are the safety precautions we should know. Listen, we have to make sure that people should not expose to radioactive radiations if there is any accident. Next, it should be shielded with, what do you mean by shield? Protected with the lead. the thick lead material, so that lead is the only material which will not let the radioactive radiations pass through it. So it has to be shielded with the thick lead material. Then the nuclear power plant is air-tighted. It should be placed in a air-tighted building. Air-tighted, what do you mean by air-tighted building? It should be made up of thick-walled building, so that it should withstand the earthquake and also the fire. Next, cooling system. There should be a backup cooling system, because we know nuclear power plant is based on a high energy. When there is a high energy, high heat energy will also be produced. To remove that, there should be a cooling system. These are the precautionary measures only for while establishing a new nuclear plant. Now we will talk about the second safety precaution, that is nothing but while handling nuclear materials. So after establishing a nuclear power plant, these are the procedures we have to follow. The people who are working in nuclear power plant, they should wear lead lined aprons and gloves to make sure they are not exposed to radiations. Next, see, if the material is there, okay, we should not use it by short tongs. Like, you cannot do it like this. The tongs, whichever we are handling the materials, that should be long. So you have to keep away. You have to keep the distance away from the material. Next, the material should be shielded with the lead. It should be covered with the thick lead box, so that it will not affect us in any way. Now we'll talk about during the disposal. First, initially establishing a power plant, during the working of power plant. Now we have to make sure the disposal is also very clean. How we can do that? It should be placed, the material should be placed in thick sask. Sask is nothing but the huge drum, okay, that should be thick, and it should be buried in a specially constructed deep underground stores, so that these radiations will not come out and harm us. Now we'll talk about the final topic, that is nothing but background radiation. What do you mean by background radiation? These are the indirect radiations. See, I'll define it. The background radiations are the radioactive radiations which we are all exposed to, even in the absence of active source. What are the active sources? Nuclear waste and nuclear radiations, right? Those are the active sources. Even in the absence of active sources, we are exposed to all these radiations, nothing but alpha, beta, gamma. What are those sources? Internal source, that is inside our body. Inside our body, potassium 40 and carbon 14 are also there. Then external sources, cosmic radiations, solar radiations. We are all exposed to cosmic radiations and solar radiations. But the main thing about these background radiations are, these are not harmful to us. These are safe. That's it. Now we have completed the concept of radioactivity part A. So immediately go for the theory solutions, then you can understand everything. So you will get to know what kind of questions they will ask in the board exams. After this, we are going to start with our part B. All these videos will be available in the description box. Thank you.